Now I want to talk about your work in asynchronous design. So in this course, I teach students that we have synchronous circuits where the circuit is advanced by a periodic clock. But you work in asynchronous circuits, and this is sometimes called clockless logic because there's actually no global clock that's sent around. They operate in a different way. So can you explain how an asynchronous circuit works and the advantages and maybe the challenges in designing circuits this way rather than as a synchronous circuit?
So sure. So in an asynchronous circuit, basically a good way to think about it is computation sort of progresses when data arrives. So instead of waiting for the clock tick to show up to say, let's do the next step, you wait for a new input value to arrive before you do the next step. So that's the basic sort of operating principle. So instead of saying, well, when the clock tick shows up, I have my new inputs and I'll produce my sort of previous outputs. Right? That's sort of the conventional way of doing things. Another way of doing this is to say, well, I'll tell you when I'm giving you a new input, so I'll have a special signal that I'm going to use to tell you a new input's arrived. And then when you produce your new output, you do the same thing. You produce a signal saying, hey, here's a new output. Right? So that's the basic difference, and that's actually a very natural way of interactions. I mean, sort of apart from sort of synchronous circuits, pretty much the rest of the world behaves this way. Right? You look at biological systems, you look at, I talk to somebody and, I hear a response based on, what I said and so on and so forth. That's a very natural way for, human beings or sort of anything to interact. And that's how most of the world works. And even in computer systems, pretty much as soon as you leave the confines of a small part of your chip, that's true as well. Right? Systems operate sort of asynchronously with respect to each other.
Now, this is even on a smartphone SoC, right? We think of those as synchronous systems, but they have asynchronous aspects to them as well.
Right, and depending on which generation of the design, there could be more or less of this in the system design itself. Another good example is sort of almost every memory today. There's a little core of it that's actually asynchronous because it turns out that there's a bit of that. Otherwise, it would be slower than it should be. You can actually go a little faster that way. So a lot of memories have this sort of asynchronous circuit built in. A lot of times it's just easier to design a system where different parts operate at different frequencies because some parts are naturally faster than others, but then they're operating with different clocks and then they need to communicate with each other, and that's also asynchronous. So those are sort of the most commonly found examples in the commercial world.
Now, this last part about you have two. I have a CPU and a memory, or even CPUs need to communicate, and they're not running off the same clock, and they need to communicate with each other, even though their clocks aren't lined up.
Right.
That's an example of asynchronous communication. But now you've done some work in this area, right? Because you have to put this through a series of D flip-flops, which delays the transfer of information between those. So you've done some work in order to make that, to improve the performance on that. Can you talk about that a little bit?
Sure. So there's a problem when actually it's sort of an interesting problem. There's essentially a fundamental problem if I need to communicate with if one part of the system needs to communicate with another part of the system, and that the part that's receiving the information is synchronous, but that synchronous operation of that system isn't related to the part of the system sending information over, right? And so what can happen is the receiver has got this clock ticking along, and the input might change sort of right around when the clock is supposed to tick, and that can create problems. It's called a metastability problem. I don't know if you talk about it in your class, but it's actually a very tricky thing to think about. In fact, it's a good example in the literature where in the initial, the 60s, people didn't even realize this was an issue. So lots of very smart people were fooled. So, it's a very tricky, subtle issue. And so typically the way you can handle this problem is, it turns out we don't know how to do this with 100% reliability. But what we know how to do is we know that if we allow this process to take longer by having multiple D flip-flops, for example, then the failure rate goes down exponentially. So you can make the failure rate to be low enough that you're more likely to, the power supply is more likely to break than,
So you can't guarantee no failure, but you can put enough flip-flops so that you can make it so small that it won't be an issue, typically.
So for all practical purposes, you assume the system's reliable, right? So exactly. So the problem with that is when I'm sending you information, I have to go through all these flip-flops, so I have to wait to receive the information. And unfortunately, the waiting is inherent. You can't get the information through reliably without waiting. But actually, what we did, which you're alluding to, is there's a way to cheat, right? And the way you cheat is even though, so the reliability issue only shows up when you finally need to receive the circuit, the information in the clocked domain. But I can view the entire process of transferring that information as going from an asynchronous domain to a clock domain. But what that means is I can compute on the logic, on the data going through asynchronously before the data arrives at the destination.
So instead of just wasting these full clock cycles, you're actually doing useful computation within those clock periods.
So you can cheat. So you can hide computation into this. You can push some of the computation you need to do onto this delay. And so even though you're still waiting, you're still getting useful work done. And that has to happen in the asynchronous domain because the asynchronous domain is ready to receive inputs whenever because it isn't being clocked. So it can just wait until the data arrives. So that's the basic idea.